Alrighty, so the first one says you have a frequency of 150 hertz. We were supposed to draw the tubes. I think so. Just draw the fundamental. Oops, that's horrible. Something like that. So you just got to make sure that's lambda over 4, and that's lambda over 2. Be prepared to draw any harmonic of these. Do you get what I mean? So like, you should be able to draw the third harmonic of this. Okay, so know what that means. Know, like if I tell you the third, the fourth, the fifth, the second harmonic, whatever, you have to be able to draw it in. Are we supposed to find the length of these tubes, or what is that? Is that what it is? Yeah. Okay. So then, of course, just using F is equal, and since it's the first one, we can just say 4L, and then F is equal to 1 over 2L. So in this case, L is equal to 1 over 4F, and L open is equal to 1 over 2F. So what's this, 1/600th? And then this is 1/300. Oh, I forgot the V. Yeah, sorry. Just kidding. Yeah, there you go. That makes sense. I'm like, that seems really small. Yeah, so then this is 340 over here, 340 over here. So this is going to be 1.13 or something. Yeah, okay, so 1.13, and then this will be like, I don't know, less than half, or a little more than half. 0.5? 0.56. Okay, questions on that one? All right, so as noted, that was a typo. The string is not supposed to be 12 kilograms, it's supposed to be 12 grams, sorry. And then how would you set this up? I would set it up in the easiest way possible. Well, technically, the easiest way possible would just be this. Hang some big mass on it if you wanted to. That would be like the easiest way possible with 1 meter length. Then if you pluck that string, it should make a certain sound. And then this is the hanging mass here. So we can say F is equal to 1 over 2L times the square root of T over mu. We can calculate mu by saying mass per length. So it's going to be 12 times 10 to the minus 3 kilograms per meter. And then that's mu. What? N is 2. Oh, the second is. So I said the question says playing the second harmonic?
Yeah.
Oh, okay, cool. That's easy. So I forgot that piece of given information. Sorry, thank you, Eric. So if n is 2, then we put the 2 here. So that'll knock out this and do 1 over L. So I can just, whatever, do the algebra stuff. And I get T will be equal to, yeah, F squared L squared over mu. Because if I put this, I'm going to get L and that FL, and I square both sides, I get FL, F squared, L squared, and divide by mu, and that should equal tension. Yeah.
Does it just say to draw it in the second harmonic, not calculate it?
Oh, I don't know. Oh, that's what he said.
It says draw how you would mount the string and show.
That's all right. No, I appreciate the information. Yeah. My fault. Should have read it better. My fault. No problem. That's fine. Whatever. It just puts this over here, puts a 4 here. So that's not that big of a deal. No worries. It all works out. So we put our 4 there, and then, I don't know, go to town. Whatever. 4 times 150 squared times 1 squared, which is not that hard. And then mu is 12 times 10 to the minus 3 over 1. So that goes away, that goes away. This squared is like 22,000 something, right? 22,500 times 4, which gives you like million something. Then, whoa, this is gigantic.
Multiplied by mu.
Did I do that wrong algebraically?
Multiplied by
Yeah, I should have multiplied by mu, not divided. So mu should have been up here, which makes life a lot better. Okay, so doing this, what do you get? So this is 1.5 times 10 to the 2 squared, which should give me 2.25 times 10 to the 4th. And then 2.25, this to the 4th, that gives you 1. So 2.25 times 12, whatever, 25, is it around 100 something? 1,000 something, sorry. I'm guessing. What is it? 1,000 even?
80.
Oh, 1,080, okay, thank you. So that's going to give me 1,080 newtons. And then if we're supposed to draw the second harmonic, then I just do this.
Is it also possible to draw it like mounted, like what Jab's gamma was like?
Sure, you could have drawn it like this. And you could have even said like this is 20 centimeters. You could have said that that's 80 centimeters. That's fine. Just make sure your L's will change appropriately or whatever. If you do this, this will give you a slightly varied answer. But, I would give. I don't think, did I say the vibrating string has to be? No, I just told you the string was that length, and you just have to produce that frequency. So you should be fine. Your answer will vary if you do this. This is one of those things where if you did it like this, as I'm trying to grade it fast, I probably won't catch it. So it'll get marked wrong based on the numbers and like just zipping over it. Like I'll probably give you the process right, but then the number, I don't want to go back through and calculate it. So like that's where when you get it back, or when you go to like make sure check on your test grade, you like look and double check on it. Okay, questions on this one? Okay. All right, so for number 3, why is it that when a race car approaches, right, the frequency goes up, and when the race car departs, the frequency goes down? Well, there's different ways that you can kind of say this. You do want to say this is because of the Doppler effect, right? But that's not that whole answer. You can't just say that. So then you'll say, because the Doppler effect, that's true, and this is what's happening. So as it's coming closer, basically the easiest way that I can think of to say this is that as an object is coming closer towards you, each new signal, each new pulse is released at a closer position, right? So if this car is racing its motor, just revving its motor at like whatever, 1,000 something RPMs at a certain distance away. And then I'm going to hear a specific frequency. But when the car is coming towards me, in between each little bup, 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 bup of the motor, right? All those things add up to be like, that's that sound. In between each little pulse, the car is getting closer to me. So the distance that those pulses have to cover is less. And if the distance is less, the time is going to be less, so then the frequency goes up. Likewise, when the car is going away from me, then that similar idea goes reverse. That each moment, the next pulse is released at a greater distance between the pulses. But the pulses are still going the same speed. So because of that, it results in that. Okay, I don't know if I showed you the equation, but just for fun,
Equation.
that's pretty much the equation for the Doppler effect. Okay.
Isn't that fine?
And then what this is saying is this and this is the velocity of sound. This is the velocity of the observer. This is the velocity of the source of sound. Okay? And then this f prime is the new frequency or the perceived frequency, and this is the original frequency.
Do we need to know some test?
I'm just showing you. So, questions on this one?
So when it's going closer to the observer, then the pulse is closer together?
Yeah. Well, the
The distance,
yeah, the pulses are closer together because they're released at closer positions. So it's like as it's that I classically that paintball gun thing. If I fire pop 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 pop, right, they're gonna have a certain distance between the paintballs. If I'm running towards before the paintball would fire, and then when the first paintball got here, the next one would fire. So then those will fly at a certain distance, and when they hit, they're going to hit at a certain frequency. But when I'm running towards the target, this paintball is released, but the shooter has moved to here. So now I shoot again. The frequency of the paintball gun has not changed, but because the next pulse was released closer to the last pulse than the other one, the distance between them is less. So when they hit, they're going to hit faster. Okay, any questions? That's a good question. Any others? Alrighty, so then let's go to the last question, which is, whoops. So something, I think, what, like how rainbow forms or something?
How do rainbows form? I've seen hydrogen.
With
Okay.
magic.
Huh?
With magic.
Yes, magic. Okay, here's a question. Where do you see rainbows? Okay, so generally we would say after a rain. But in fact, what has to be happening for rainbows to occur?
Must be Ireland.
Yeah, there must be rain,
And Ireland.
just not where you are. Do you get what I'm saying? And the reason there's lots of rainbows in Ireland is because it rains all the time. And the weather on the North Atlantic Ocean is really,
It's
really sort of tempestuous. Like it comes in and goes out, and comes in and goes out. So you'll get that. But what you'll discover the next time you see a rainbow is that there is still rain going on somewhere. So water droplets are falling through the air. Okay. So as these water droplets fall through the air, then the sunlight that comes at them, right? The sunlight is going to hit like here, and then it's going to hit here, and does this, and then it breaks apart into this sort of prism. Now, because raindrops are shaped like what? Yeah, they're like circles, right? Smaller raindrops. Big raindrops, when they fall, might be different, but small raindrops, like little tiny drops of water. Because where else can you see a rainbow? Not just...
Oh, like where you sprinkle it?
Yeah, when you
Haven't you ever seen a rainbow in the summer, walking down the street, somebody's sprinklers going off?
Everybody green, you're running through it.
Right? So you see a rainbow on a sprinkler, right? So it's not because there's tiny little leprechauns, like, you know, sort of the low red poor leprechauns that
Like
just
tiny-
set up their little houses and your bushes and what's that?
He's asking for your opinion.
Yeah. So, but the curve of the rainbow is because of that. And then the other factor is you see it based on, or you see it a certain way based on your position. And hang on, let me see. Here we go.
Whoa, what is this?
This is called Google.
Wow! What black magic
Okay.
is this?
So, do you see what color's on the bottom, what color's on the top? Right? Purple's on the bottom, red is on the top. Why?
Because purple is faster.
Purple's faster, which causes what?
cause it to go another angle?
Yeah, purple is faster. So when it enters the new medium, being the light, it bends more. So what happens is here, this beam is purple. This slower beam is red. And then the rainbow goes there. So you stand here and see this rainbow, and when you look at it, it's purple on the bottom, red on the top. That's why rainbows look like that.
That's why they curve too.
Yeah, the curve is because of the water droplet. Right? You've seen rainbows on the wall, like when light shines through like a chandelier
Yeah.
or light. Are those bent? No, they're straight because what's happening is that light is going through the prisms that are in the chandelier on the wall. In fact, it depends, right? If your chandelier has weird curvy lines, then your prism on the wall, your rainbow, sorry, not the prism, the rainbow on the wall will be like wavy. So it's all a function of what the light's passing through. So why do rainbows form? Okay, there has to be sun over here. Sun. Okay, well, okay, let's redo this. It's kind of like there has to be sun over here. And then at some point, there has to be like all this water coming down, right, in the form of little droplets that I don't want to draw. Okay, and then you're over here just minding your own business, right? And the sunlight, which would normally come to you like this, is going through these little raindrops, right? And actually, it would be the ones up here. Like this light would normally go away from you, yes? You wouldn't even see it. So what you might see is clouds, you might see houses, whatever, like all this stuff. But here, when this light goes through, you get the you get the bending, and then this shines down at you, and you can see the rainbow. So this is why you can never. Why can you never find the end of a rainbow?
Because the Irish are running away with their gold.
So why can you never find the end of a rainbow?
Because you are at the end of it.
Yeah,
Because it's like always moving kind of.
yeah, because you're always going to be in the middle of it.
Oh.
If you can see it, whenever you move, you'll always be looking at this. Have you ever looked up and said, "Oh, look, there's a rainbow," and it's like, whatever, it's like this. Like I can only see this much of the rainbow, right? You always see the full arch, right?
See that
Or
on
some little
TV.
tiny thing. Yeah, well, that's kind of digital, whatever, but. Right, and if you see something like that, it's okay. These
So
are really-
what was that?
Oh, look at this. This is brain damage person.
What about those like seeds of light?
What?
What about these?
Like there's a double rainbow right there.
Oh yeah, double rainbow. Okay, so how could a double rainbow happen?
The light's weird, so all the rainbow rain's like not here, so it's back to
My guess. Let's see. Let's go back.
Good editing.
Let's check out that
Okay.
Okay. Let's think. I haven't really thought about it. So let's think about this. If the light comes like this, then that's going to break into this, and you're going to see that. So what would cause another one to break that way? The light. It's yeah, that's what it is.
Maybe he just edited the video.
Or,
Image.
that's my guess. Like there's some sort of cloud layer, and light is bouncing off the cloud layer and going through the rainbow, the raindrops.
So what about an aurora?
So the whole issue is like the raindrop is like this, right? So if light comes like this, it hits here, disperses, bends, and that produces this rainbow. Roy G. Biv. Does that make sense? So how do you flip this? Here's the raindrop. What do you have to do? Yeah, the light has to hit like this. Then here's Roy G. Biv. So how do you get that to happen? Here's this droplet. Here's that droplet. The only thing I can think of is this droplet is straight sunlight, so you get the one rainbow. Then there's light bouncing off of here, and then you get that rainbow.
What about
Aurora are different. Aurora, whether it's borealis or whatever, I can't remember the one from the southern hemisphere,
I think the term is like
Australis or something. I don't know. Whatever the southern, they're high energy particles. It's like
lack of that atmosphere.
yeah, it was. And the reason they happen in the North and South Pole is because the Earth's magnetic field goes like this. So then the solar energy, like solar wind, when it hits the outer
It's
atmosphere,
Australis.
Australis, yeah, I knew it was something like that. When the solar wind, all these high energy particles being sort of expurgated from the sun, when they hit the Earth's magnetic shield,
Earth.
okay, when they hit the shield, they kind of blow around it, right? The Earth is tilted, so when they hit in that cone, then it gets concentrated. That's why you can see it at the North and South Pole. If you go up to the outer atmosphere, then I believe you can see that happening. You can measure it. You can see the really high temperatures that are going on and all that kind of stuff. So, but at the North and South Poles, because of the curve of the Earth, like these cones, so then when the solar wind hits in there, it intensifies the effect, as you can see. Yeah.
So there will be no way for us to see the end of the rainbow. Like we never see it.
Nah, because if you move, like if I see it now, I go over here, I don't see it anymore. Because the sunlight that's coming this way is making it. Because there's water between me and the sun. If I step here, there's no longer water between me and the sun, so I don't see a rainbow. All right, questions? Does that make sense? It's interesting. I've never tried to think out how a double rainbow happens. I don't know if that's the right explanation, but it seems reasonable. Okay.